Okay, welcome back, everyone. It's time to continue our lectures. So last time we talked about three-dimensional space and vectors in three-dimensional space. So we discussed Cartesian coordinates, coordinate system. So every point in three-dimensional space is given by a triple of numbers x, y, and z, exactly in that order. You'll see later today why order is important. And the you can, in order to depict a point in three-dimensional space, you would draw a parallelepiped with one vertex, which is inscribed into the coordinate frame, and then one vertex is at the origin, and the opposite vertex will be at the point P with coordinates x, y, and z, which you want to study. Then we talked about the distance formula. So the square of the distance is sums of squares of coordinates. So OP squared is equal to x squared plus y squared plus z squared. Then we talked about equations of simple equations of planes. So how to give an equation for a plane. So there are some simple examples, and then we sort of promised that any plane will be given by this equation. So it's a linear equation in A, B, C, in X, Y, and Z. So any plane can be parameterized like that. So that's our plan for today's lecture, maybe also for Thursday after we're done the quiz. Okay. Yeah, and then we looked at spheres, ellipsoids, parts of spaces that are covered by those shapes. And finally, we turn to vectors, right? So in a nutshell, vector is a directed segment, right? And as well as a set of all parallel vectors which are parallel to it and have the same length, which means that the vector has a tail and a tip, and then we are free to move it parallel to each other in space wherever we like. We talked about vector addition, multiplication of vector by a scalar, and we described and then vector subtraction. And we described all these three operations in terms of coordinates of vectors, right? So to do vector addition or subtraction, you simply add or subtract the respective coordinates of each vector, and to multiply it by a scalar, you multiply every coordinate by that scalar. Okay, and finally, we talked about properties of vectors. So basically, you can add them commutatively. There's a zero vector which has no direction and zero length. Yeah, so there's a unit if you multiply vector by one, you'll get the same vector. And finally, we talked about coordinate vectors, so I, j, and k, which have coordinates 0, 1, 0, 0, 0, 1, 0, and 0, 0, 1, respectively. And every point and every vector in three-dimensional space can be written as a sum, which is also called, I'm sure you know this word from linear algebra, this is called linear combination. So it's linear combination of vectors I, j, and k. Sort of linear means that it's a linear function, right? So basically it's the sum of those vectors with some coefficients. Yeah, that's what linear combination stands for. Okay, are there any questions about this? Good, so if no, then today's lecture so today's lecture 6. So we will cover materials in sections 12.3, 12.4, well, and see how much time we get. And we'll talk about dot product. Well, I'm just going to write them in commas. So dot, cross, and triple products. So somebody asked me yesterday, can we multiply vectors? Well, the answer is yes, but because they're vectors, there is more than one thing that you can do, right? So the simplest product that sort of the most yeah. So one thing you can do is so-called dot product. Or sometimes it's called also scalar product. Well, scalar is opposed to the vector product, and then the cross product is also sometimes called vector product. So it's a scalar product. Another adjective is inner product. This is how it works. So let's say you have vectors A with the coordinates A1, A2, and A3, and vector B in 3 dimensions with coordinates B1, B2, and B3. Let's write it as a formal definition. So let A and B be these vectors, then the dot product of A and B is the following thing. So it's denoted as A dot in the middle, A dot B, and is given by the following thing. So it's a scalar. So it's A1 B1 plus A2 B2 plus A3 B3. Yes, it's the same as scalar multiplication. Yes, so scalar product or scalar multiplication. Yes, product or multiplication are synonymous words. So this is what it does, right? So it takes 2 vectors and just multiplies first component by the first component, then second component by second component, third component by the third, and then adds these 3 terms together. Okay. So the good. That's what. So let's look at some examples. Let's take vector A is equal to 1, 1, 2. Vector B is equal to 2, 7, minus 3. What is A dot B? Can you calculate? Three, right? So let's see. So yes, this is 1 times 2 plus 1 times 7 minus 2 times 3, right? So that gives you yes, it's 9 minus 6, so it's 3. That's right. Julian, what are these numbers? So it's a sum, it's a number, right? So the result of a scalar product is a number, it's a real number, right? So you take 2 vectors, you have this 6 numbers, and you make 1 number out of 6 numbers by doing this thing, okay? So we will get a vector, but that comes in the cross product, in the vector product. Not yet, okay? So the scalar product is actually a number. Okay, let's do one more example, just for fun. let me give you a vector in a different space, right? It's in four-dimensional space. So A is four numbers: 1, 0, 1, -1, and vector B is 0, 1, 1, 1. What's A dot B? Well, I didn't define it, but basically you have to. If you have four coordinates, you just multiply first by first, second by second, and then you just add them together. Yep, 0, indeed. So you have 1 times 0 plus 0 times 1 plus 1 times 1 minus 1 times 1, and everything cancels, right? Everything is equal to 0. So indeed, something special happens when the scalar product is equal to 0. We'll talk about this in a second. So yeah, now, well, let's list the properties of the dot product. Right. So first, if you take A and do the dot product with itself, what will we get? You'll have, so let A be is equal to A1, A2, A3. Let's say we live in 3 dimensions. Well, by definition, it is A1 squared plus A2 squared plus A3 squared, which is, as we know, is the length of the vector A squared, right? So it's absolute value of A squared. So it's a convenient way to represent the absolute value of vector, is just taking the dot product with itself. So that'll be the square of that. Number 2, there's distribution law. So if you take A dot B plus C, everything follows from the definition, right? So these are simple properties. So because you just take the product of components, then of course you can just do it like this. So A dot B plus C is equal to A dot B plus A dot C. Then of course it's commutative, right? So A dot B is equal to B dot A. Well, again, follows directly from the definition. And then you can also multiply, if you multiply the vector by a scalar and dot it with another vector, it's the same as multiply scalar by the dot product. Okay, and then finally, if you take a 0 vector, so with components 0, 0, 0, right, and dot it with A, you will get 0. Okay. Now, let's talk about geometric interpretation. Are these related to matrices? Yes, you can write it good. So, as I assume most of you took linear algebra, so indeed, you can represent, if you represent vector A as a matrix like this, A1, A2, A3. So it's a matrix 1 by 3. And then you can take vector B, let me put, actually that should be transposed, right? So, well, so let me give you the matrix, well, just to not abuse notation, let's call it A, it's okay, yeah, so now, let's say there's a matrix A transposed, and then there's matrix B, which is just the vector itself, right? So B1, B2, B3, right? So then you can show that this thing on top is equal to the product of matrices A transport times B. Right, so it's if you multiply the row by the column, you get on the matrix which has on the, you see, if you multiply 1 by 3, matrix 1 by 3 by matrix 3 by 1, you get a 1 by 1 matrix, which is a number. Okay? Yeah, it's a good question. Yeah, in fact, we'll use vector presentation later. But yeah, that's right. So yeah, so there's a way to do it using linear algebra. Okay. Now, another sort of application of of the dot product is to study angles between vectors. Right. So just so here's the theorem. But not more than just a calculation, but nevertheless. So the following thing is true. So if you have two vectors, A cross B, A and B, and then their dot product is equal to the, because it's a number, right? So there is a very specific way to represent that number. So you take vector, so A cross B, A dot B, excuse me, is equal to absolute value of A times absolute value of B times cosine of the angle theta, where theta is the angle between A and B. So if this is A and this is B, and they make an angle theta between each other, so it's really like you put two tails together and measure the angle. So there's a it actually I made a mistake here. I'm sorry. So the mistake is there's a mistake in the picture. I'll just swap about the mistake. So the angle theta that is drawn here, so it matters because cosine of theta can be either positive or negative depending on the angle. It does matter which direction you measure the angle. So it's angle between A and B, right? So in this case, theta is a large angle. Maybe give another example. So A is this and B is that. And we'll look at A, B, and here's the angle. So you measure it counterclockwise, as we did in polar coordinates, from the first vector to the second vector. This is more than vector. Yeah. So let's see. So let's prove the theorem, right? So well, let me draw complete the triangle. Say we move everything to the origin of the coordinate system, and then this is point A and point B. And just complete the triangle. So I believe you know this formula from grade school, right? So if you have a triangle, so in a sense, it's a generalization of the Pythagorean theorem when angle is not straight, right? So the straight of this so AB is equal to point A squared plus OB squared. And now, if the angle theta was right, it was 90 degrees, that would be it. But if not, then there is a correction term, right? That there is this double product here. So Sharon, I'm coming to that, right? So it's still true that the A dot B is just sum of three numbers, three products. What I'm telling you is that this sum, this answer can also be written as such. So it's the same thing, right? So that is also equal to A1 B1, A2 B2, A3 B3. both are true at the same time. Yes, Julian, I believe it's called law of cosines. Yeah, so, and then you just need to, rewrite this in terms of vectors, right? So what is AB in terms of vectors A and B, right? So remember, so this is vector A, and the picture is a bit dense, make it simpler. Right, this is B. So how can we represent the segment AB in terms of vectors little a and little b? So what is this vector here? Well, let me put the arrow in the middle. So it's like that thing that directs from A to B. We talked about it yesterday. So the how to represent AB, how to represent vector. This vector as C. Well, I mean, you can name it C, right? But A plus B. Are you sure? Are you sure that it's plus G1? B minus A. So let's check. So you think this? Yeah. So you have to. So you should be default, right? So if this is B minus A, then indeed. So if you add A with B minus A, you'll get B. That's right. So AB's vector is, switch the color, is B minus A. We could have taken BA, it doesn't really matter. Yes, that's J, I think it's B minus A. It's not going to be important for the calculation, but you see, what should happen is that the OA plus this, right? So that plus that should be equal to B, so therefore it should be B minus A. Okay. All right, so, and then, well, OA is, of course, so this is vector A, this is vector B, so this is A, this is B, and AB is B minus A. So you can rewrite it as B minus A absolute value squared is equal to absolute value of A squared plus B squared plus 2 absolute value of A times absolute value of B times cosine theta. Can you explain why it's B minus A using the parallelogram method? Because I'm confused. Yeah, so the so that's A. What is all the triangles? So let's say you have you add two vectors, right? So the black vector is. I reached the bottom of the page. Yeah, so so this is A. Let's just check that the formula is correct, right? This is B minus A. And now you add them together, right? So and if you do, you get a vector like this, which would be what? Which would be A plus B minus A, which is B. So blue vector is B. Is B always the greater vector in the AB? I'm not sure what greater means. So the reason why it's B minus A, not A minus B, is because we have chosen the direction, right? So you can flip the direction. You can do like this, right? And then it will be A minus B. But it doesn't really matter. The answer for what? Negative. Oh yeah, sure. No. So no, magnitude cannot be negative. So see, right? So the thing is that absolute value of B minus A squared is the same, right? So the reason why the direction doesn't matter because this is the same as absolute value of A minus B squared. Actually, let's see why. Let's just do the calculation. Cameron, does it answer your question? No. the one above, b minus a. So what can be negative? The answer for what? Well, it depends what you call it. So if AB is a vector, a vector has three components, right? Some of them can be negative, all of them can be negative, that's fine. Absolute value is always non-negative. So for example, if you have, so this vector here always have negative components, right? Because it has negative x and negative y. Okay, so let's do the calculation. So by the property of which we have proven above, right? The b minus a absolute value squared is b minus a dot with itself. Okay, well, again, if you look up to our list of rules, so here we use the rule, so rule number one, we just used rule number one, and now I'm going to use rule number two with this distribution laws. In other words, I can just open up the parentheses same way as I usually do. So that will be b squared, right? So minus, and then because it's commutative, it doesn't really matter. So I can write it as 2b a plus a squared. Oh, sorry. It's going to be a dot product. Yes, b times a. Okay. Here's that. Should have enough space to do. So that's the left-hand side of the equation, right? And then the right-hand side is whatever it is there. So let's write it down. So on the left we have absolute value of b squared minus 2, and then yeah, b dot a, which is the same as a dot b, plus absolute value of a squared, and that's equal to absolute value of a squared plus b squared plus 2 ab cosine theta. Right, and then we can cancel a couple of things. There's b and a on the right, on the left. Well, I forgot the sign. Oh, I'm sorry, nobody caught me here, right? So the way cosine rule works, there's a minus here. Otherwise, you won't get the right answer. Right? Yeah. So G1 saying, yeah, that's right. Yeah. Oh, I missed that. Right. So some of you are indeed vigilant. Yes. Right. And then because of this minus, everything is okay. So in other words, and then yes, so the theorem follows from here. Right? So that a dot b. So I swap the order because it's commutative. It's equal to absolute value of a times absolute value of b times cosine theta. Yeah, so we have proven the statement, which can be also sort of, you can solve this for the angle. So you can say, so you can use this for the following calculation. So say you are given two vectors, a and b, with given components. So you can easily calculate its dot product. And you are asked, what is the angle between these two vectors? Well, now we know the answer. So the angle between a and b is, well, rather the cosine of the angle, but what is it? Yes, so the cosine of the angle, the cosine of the angle between b is, so it's the a dot b divided by absolute value of a times absolute value of b. And then we actually want angle in radians or degrees, you just take the inverse cosine. Okay, let's look at a couple of examples, right? So before the intuitive one, right? So you have, see, one of the vectors is this vector I that let me first give you the two-dimensional example, right? So we have x and y, right? And then there's a vector A with coordinates a1 and a2, right? And I is our usual thing. It's 1, 0. So and then this angle is theta. Well, if you do the dot product, right? So if you do a dot I, right, you get a1 times 1 plus a2 times 0, so it's equal to a1, right? So therefore, from here it follows that the cosine theta is equal to a1 divided by the length, the absolute value of the vector a, which is equal to a1 squared plus a2 squared. And there's, of course, the formula that we already know in polar coordinates, right? So when we have theta here is the polar angle, and its cosine is basically it's the cosine of this angle, which you can find by calculating the x component of your, basically x divided by r, right? So, so previously we know this formula as, it's the same as we had before. It's what is called x divided by r. Only now, of course, we can do it. We can easily find cosine of the angle between any two vectors anywhere, right? So we just plug numbers and we find the angle. Okay. Now another example is, let me lift it up a little bit. We did this calculation here, and then the answer somehow turned out to be 0. This example. So in this case, the dot product of two vectors was 0. Question: how did you get square root? Oh, it's the, so if you have a vector, so if you have a vector with its components, right, its absolute value, length of the vector is square root of a1 squared plus a2 squared. Talked about it yesterday, right? And today. If it's a vector in 3 dimensions, you just have some of those. Yeah, yeah, just the Pythagorean theorem. Now, so yeah, in this example, well, I'm not going to scroll back, but anyhow, so if the dot product is 0, well, what does it say, right? So if it happens that a dot b is equal to 0, then from our formula it says that the cosine, and then assuming here that a is not equal to 0, right? So that a is not a 0 vector. So a is not a 0 vector, and b is not a 0 vector. Because if they are, everything is just 0, right? So then cosine of theta is equal to 0. So that means theta is what? It's either pi half or 3 pi half. So in other words, the angle is either 90 degrees or minus 90, right? So if the one of these two situations is realized, right? So it's either this, so this is B, and this is A, or the other one, right? So, or the other one. So therefore, regardless, this vector is 90 degrees. So these two vectors are orthogonal to each other. So we can make a statement that A and B, well, A is perpendicular B, A and B are orthogonal in the sense that the angle is either 90 degrees or, oh yeah, thank you. I got distracted by some message. Like that. If and only if A dot B is equal to 0. Guys, yeah, so it shouldn't be denominator multiplied by square root. Denominator of what? I don't understand the question. Oh, I mean the, yeah, but like the, yeah, so that's what I was saying. So the, well, first of all, denominator does not change the fact that numerator is 0. So if fraction is equal to 0, it only happens when the numerator is 0. What you need to check is that the denominator is not 0 at the same time. What I'm telling here is that if vectors are orthogonal to each other, so you need to make a adjustment that if you have a 0 vector like here, then it's orthogonal to any vector, right? It's just an assumption. Yeah, so you don't have to divide, but I mean, that's the formula for the cosine, but to show that vectors are orthogonal, it suffices to look only at the numerator. Okay, guys, I need a couple of minutes right now. There's something came up. I got some urgent message. I'll pause. So let's pause for 5 minutes. Okay, like 3 minutes, and I'll be back in a moment. Okay, sorry for that. It just take a moment. Oh, yeah, I'm back. That was quick. I wish all bureaucracy problems were solved like that in the 15 seconds call. So where are we? Daniel, did I answer a question or not quite? Yes, okay, let me reiterate. So if you have a dot b equals 0, when can this happen, right? It can happen, yeah, it happen in 3 different instances. First, a equals 0. Then a dot with any vector is 0. 2, b is 0. And of course, they can be 0 at the same time. And then the third instance, which is a bit more interesting, is then when vectors are orthogonal. Now, you can extend the definition by saying that, well, you can just declare that a zero vector is orthogonal to any vector. It makes sense because, well, we just want to have a more universal fact about sort of, we can just sort of we make it work, so we can make the statement, right? So vectors are orthogonal if and only if. So there are two parts in the statement. There's if part and only if part. So if the vectors are orthogonal, then a dot b equals 0. How to make a statement backwards? If a dot b equals 0, then either a equals 0 or b equals 0 or both, or a dot b equals 0. So we just want to say that zero vectors are orthogonal to every vector. Okay, so there's the follow-up. I meant for the vector times b vector over the magnitudes for finding. Yeah, but you see, so cosine theta is a dot b over ab, absolute values. If this is 0, then you can only look for the numerator, right? So we have already excluded the cases when the vector is 0. Exactly, that's what I'm saying. So let's. I'm just gonna reiterate. So don't look at this formula, right? So basically saying, if let's say so Sharon and Daniel and others. So if let's say that none of the vectors are 0, so a and b are non-zero vectors, then if a dot b is equal to 0, then the angle is 90 degrees because we can write this formula and we know that the denominator is non-zero. Okay, so if denominator is non-zero, then to show that the fraction vanishes, it suffices to look only at the numerator. Okay. Now, assume that one of the vectors is a 0 vector. Then we just say that 0 vector is orthogonal to any vector. So to make this inference, I don't look at the formula, right? So I just say it's a part of the definition. So you don't need to do it. You don't need to take any limits or anything. Yes, the expression is undefined, and that's why we're not using it. Yeah, so Daniel is okay. So Sarah. Good. Yeah, so that was the dot product. Okay. Good. Okay, now let me move off to new page. I believe I forgot to upload the slide, but okay, so okay. Now let's talk about another application. These are directional angles. This is what it is. And so you do say we have a vector in space, and there's this point P with coordinates x, y, and z. Let's say R is its magnitude or absolute value, so R is square root of x squared plus y squared plus z squared. And now I want to measure the angles between this vector and the coordinate axes. So like there's an angle between x and r, there's an angle between y and r, and there's a vector between Z and R. We could call them alpha, beta, and gamma. Well, we can easily we know we can easily find what these vectors are, right? So because we have a convenient description of unit vectors in each of the directions. So there are vectors I, J, and K. So if you do this vector OP dot with I, right, then we get X, Y, and Z. This vector dot with 1, 0, 0. That gives you X, right? Well, by definition of the angle, we can say that cosine theta is equal to, well, that, so it's X divided by R. Right, so it's similarly cosine, sorry, not theta, alpha. So similarly, cosine beta is equal to Y divided by R, and cosine gamma is equal to Z divided by R. Right, so that allows us to write the components of the OP vector in a different way. So it's equal to, it's like R times cosine alpha, R times cosine beta, R times cosine gamma. So it's like you fix the absolute value and then you just select the direction where it goes. Okay. So that's one definition, which is can come handy later. Now, another one is another sort of useful tool is to calculate projections. So I already showed you one example. So say you have vector A, like that, and then there's a vector B, which goes this way. So you want to calculate if you do this right triangle between A and B, and you want to calculate the length and also the vector, which is formed by, which appears in this right triangle, right? So we want to call this a projection. Projection of B on A. And we want to make two definitions. One for the scalar, so just for the length of this segment in this right triangle, and for the vectors, just sort of assuming that it's collinear, it's in the same direction with A. Right. So this is how we do it. So the one of the notions that we introduced is scalar projection. Right, of B onto A. That's how we're going to call it. Which is given by this formula. So we take the A dot B, right, and then we divide by absolute value of A. Let's see what it does, right? So A dot B, if this angle is theta, then A dot B is absolute value A times absolute value B times cosine theta divided by absolute value of A, right? So that's simply B times cosine theta, which is of course is the length of the segment, right? So this projection is actually measures to B times cosine theta. Is this similar to Gram-Schmidt rule? Actually, yeah. So when you do Gram-Schmidt diagonalization, you would calculate the projection, and then you would subtract it. Yeah, that it's a very good comment by Cameron. So only here we're not going to do it. We're not going to do the next step. We're just going to calculate the projection. Yeah. So it's good that you know the rule. Right, and then how about the vector? Well, to get to, so yes, and I'm just going to write the definition. So it's called component. This comp, so it's comp of B onto A. And so that's one piece of the definition. And another, if you want to find the vector part, right? So let's introduce the following vector. I'm quoting green. So if you take vector A and then divide it by the absolute value of A, what is it? It's a vector which has unit length, right, by construction, because we just divide by the length, right? So if you calculate the length of A of absolute value of A, you get 1 by definition. So this vector here, so it's a unit vector in the direction of the vector A. So if you want to find a vector projection, this is what you need to do. You write projection of B onto A, which is now it's a vector quantity, and you just take this component, which is a scalar, and multiply it by the unit vector in the direction of vector A, right? So we just do A dot B divided by A times A divided by absolute value of A. And if you wish, you can well, put them under the same. You can write it like, so it's A dot B divided by absolute value of A squared times A. So this thing is a coefficient. It's a scalar. It's a scalar that multiplies A. Multiplies Good. So yeah. Yes, so you can see using this technology, it's easier to do the computations. Okay, finally we're going to cross product. Cross or vector product. Right, so let A be equal to, I think, A1, A2, A3. Now, here's important difference between cross product and dot product. Well, there are plenty, but sort of probably the most important one is that cross product, defined as such, only exists in 3 dimensions. You'll see in a moment why. In fact, yeah. And then B1 is B is equal to B1, B2, B3. Then by definition, so A cross B is the following vector. So it's it has component A2 B3 minus B3 A2, comma A3 B1 minus A1 B3, comma A1 B2 minus B1 A2. Well, I mean, if you haven't seen this before, that may look a bit strange. Let me show you immediately how to understand that formula. So, because you guys know linear algebra, this is also equal to the following. So, let's make the following matrix 3 by 3, and we'll calculate its determinant. On this, let me keep the first row of the matrix empty for now, but in the second row, I'll put the components of the vector A1, A2, A3. On the bottom, I put B1, on the third row, B1, B2, B3. And in the first row, I put the basis vectors. I put those unit vectors I, J, K. Right, it may sound a bit unusual to put vectors in this calculation, but just think of it as a symbolic operation. And now we'll calculate this determinant using the expansion over the first row, right? So according to the rules of linear algebra, what first, if you take this element and we cross out the first row and the first column, and then calculating the minor, like the determinant of this matrix. So it will be I times A2B3 minus A3B2. Now, in the determinant formula, there's some combinatorics with signs, right? It will be minus J times its minor, right? So the minor will be, so it's the first, it's so when you do J, you take the sort of matrix formed by first and third columns. So that's U minus J minus A1 B3 minus A3 B1 and plus K times the remaining minor A1 B2 minus A2 B1. And now you want to compare this formula with the above. So this is the first component, right? This is the second component with a minus, right? So there's a minus here. If you put it inside the parentheses, it will match the second component, and the third component matches the third component. So a cross product of two vectors is a vector, right? So you can think of it as this operation cross as, well, something that takes vectors in R3, takes another vector in R3 and maps it again to R3, right? So it takes vector A from here, takes vector B from here, and it maps them to this A cross B, which is again a vector. Oh, it's minus J because that's how determinants are calculated, right? So if you have a matrix n by n and you calculate the determinant, so the formula, there's a -1 to the n in the formula, right? So you take the an element in the first row or any row, and then if you take ith element, you multiply by -1 to the I plus 1. Right? For the vector times b vector, you wrote A2B3 minus B3. Oh, second. Yeah, thank you. It's backwards. It should be minus B2A3. Yeah. This cross product only works if vectors span R3, right? Yes, that is correct. Yes. That's what I'm saying. So R3 is a space. It's a three-dimensional space, space of vectors in 3 dimensions. As we discussed yesterday, so every point in 3 dimensions, right, is because you can always draw a vector between the origin and the endpoint. And excuse me, you can. There's a one-to-one correspondence between points in 3 dimensions and vectors, right? Because you can always draw a vector from the origin to any given point. So yeah, here I think of R3 as a space of vectors. So yeah, so it's important that cross product only exists in 3 dimensions. You write it down. Whereas dot product exists in any number of dimensions. Okay. Good. So Well, I mean, yes, we can do some calculations, so some examples, but let's first show some prove some properties. Okay. Will the cross product be orthogonal to its components? Yes, that is the case. Yes, so we'll prove it in a second. What are the signs in front of vectors I, j, k on the right? So it's plus, minus, plus. And so here it's with I it's plus, with j it's minus, with k it's plus. And then, so notice that the second component is a1, b3. So in the vector here, it's a3, b1 minus a1, b3. But here it's a1, b3 minus a3, b1. But then there's extra minus, so that's why it matches. Of course, like the definition is such because the formula with the denominator works. Okay. Now, yeah, let's. So what Cameron was referring to, sort of claim or proposition. Right, so that the cross product is orthogonal to both vectors. Will this always be the same where j would be? No, j is not x. J is the, so when you have a three-dimensional, j is a very concrete thing, right? So so we have these three basis vectors, I, j, and k. Vector j has components 0, 1, 0. It's fixed ones and vector I has components 1, 0, 0. Vector k has components 0, 0, 1. So j is the unit vector that points into the positive y direction always. There's no ambiguity there. That answer the question? I don't understand. So, do you agree with the calculation of the determinant? Okay, so now j here is something fixed. It's this vector 0, 1, 0. There's no condition if it's negative or no negative. It's just it's a j multiplied by this coefficient. That's it. Good. So proposition is that A cross B is orthogonal to A and B. Okay, well, how do you prove that something is orthogonal to something? We calculate the dot product. So let's take A dot A cross B. And then we just use this formula we just talked about, right? So A has components, so it's A1 times the first component, which is A2B3 minus B2A3 plus A2 times A3B1 minus A1B3 plus A3 times A1B2 minus B1A2. And I'll just open up everything and everything should cancel. So it's A1, A2, B3 minus A1, A3, B2. I'm just reordering terms. Plus A2, A3, B1 minus A1, A2, B3 plus A1, A3, B2 minus A2, A3, B1. So I think this goes here. A1, A2, B3. This goes there. And this goes here. so it's 0. And then analogously, B dot A cross B is equal to 0. You can do it by exercise. As an exercise, Rohan, I know that this is after. Yeah, so Rohan is asking about the quiz. So quiz will be tomorrow, not on Thursday. So this is a short week, so we cut the Friday. So the Thursday is reserved for discussions on this week. So quiz 1 will be covering the material of section of chapter 10 of the first week. Yeah, I mean, it says Thursday, but like it's we have an exception this week, right? So it's I told you that this is because of the holiday, this week is short. Simple example with a cross product. Yeah, I'm coming to that later. Yeah, sure, absolutely. Okay. So first, A is orthogonal. I just want to make a couple of statements before we go. So what is so right? So if you have two vectors, now let's try to reconcile how is this possible. So we have two vectors A and B. How is it possible that A cross B, this vector, is orthogonal to both vectors, no matter where they are? Well, the only way out is that it's actually lives in it's orthogonal to the plane where these two vectors live. Right, so every two vectors, they provide you a plane, right? Because if you put the tails together, right? And then the A cross B vector, A cross B, is orthogonal to both, right? So therefore, it has to be orthogonal to the plane where these two vectors are, because it has to happen for every two pair of vectors. Okay. So it goes into the third direction. Okay. So that's first kind of first part of the geometric meaning of the cross product. Then let's try to calculate. So right, so the direction of the cross product is it's a vector that is orthogonal to the plane where the A and B vectors are. But now there's the choice. We can go either up. It can go either up or down. So should I put which direction is realized, right? So shall I, because both vectors are orthogonal, right? So and then in 3 dimensions, each plane in 3 dimensions divides space into two parts, right? So the vector can either go this way or it can go that way. Well, let's try to figure this out, right? So for that, we have another proposition. Namely that the did I want to say that first? Oh yeah, so it is, maybe let's do the direction first. The two vectors, let's see, so the, yeah, okay, we'll do the proposition later. Now, let's talk about orientation first. So say there's an angle theta between those vectors. So and again, it's a vector that we measure the so we do it counterclockwise, right? So from A to B. So if theta is the angle between A and B. So it was important. It was not important for the dot product, but it is important for the cross product. And then now the direction of the A cross B is determined by the so-called right-hand rule. So the way you do it, you take your right hand and then you put the vector A along the thumb, vector B along the index finger, exactly in that order, and then the middle finger, which is orthogonal to the plane of your hand, of your palm, should show the direction of the cross product. So it's crucial that it's actually the right hand. Let's see why, right? So let me illustrate why this should be the case on a particular example, and that would sort of illustrate you the right triple in the coordinate system. Draw the system of coordinates again. X, Y, and Z. So let's take our basis vectors I, J, and K. So, and let's calculate the cross product of I and J. Right, let's use the formula. So formula says what? You take I, J, K, right? And then vector I is 1, 0, 0, vector J is 0, 1, 0. So out of 3 minors, the only non-zero minor will be the one which goes with K. So it's K multiplied by 1, right? Because the determinant of this matrix is equal to 1. So therefore, if you sort of if you put that's the angle theta here, which in this case is 90 degrees, right? So if you take the thumb along the I, index finger along the J, so then the middle finger will go along the K. Right. Now let's calculate them in different order. Let's calculate J times I. Well, that's what's going to happen. We have I, J, K, and it's first I put J, right? I put 0, 1, 0, and here it's 1, 0, 1. Again, the only non-trivial minor will be this, but now it will contribute with the minus sign. Right. So if you're measuring angle between J and I, what you actually need to do is to do this angle. So that will be your angle theta. Well, the formula tells you that the answer is equal to minus K. So the answer is opposite. So I cross J is equal to negative J cross I. In fact, it's true for any two vectors, right? So the cross, if you swap the order of vectors in the cross product, it costs you the sign. So A cross B is equal to negative B cross A. Why is that? Can you explain? I'll be back in 1 second. So you can, the question is why this is true. Charlotte, what are you scared of? What is that? It's okay. You know, it's really like I mean the idea is to do it step by step. Like every statement we're making is not too complicated. It just if you look at the whole pattern, it may look a bit overwhelming, but like each step is not that hard, right? So let's look at the definition, right? So of the cross product. In fact, in a sense, it's a question about linear algebra. Once we understand how the so proof of this proposition comes from the definition, right? So A cross B has I, J, K, so it's really handy formula here. It's A1, A2, A3, B1, B2, B3. So what happens if you swap the order here? You are swapping the order of this, right? You swap in two rows in the matrix. What happens with the determinant if you swap two rows of the matrix? Yeah, what happens with the determinant of that matrix if you swap rows? Yeah, absolutely. That's why it's true. It's as simple as that. So it's yeah, it follows directly from the definition and from the properties of the determinant. Okay, so we'll talk about the quiz in a moment. Let's finish off with the scalar product, and then I can answer some quiz questions. Okay. So with the cross product, I just don't want to leave it in limbo. Yeah. So there's that. Then how about the magnitude? Right. So another proposition is that the absolute value of A cross B is A absolute value of A times absolute value of B, and now it's times sine theta. And theta here is assumed to be between 0 and pi. So in other words, if you are in a situation where there's like the orange theta, right? So if you have two vectors I and j, in order to calculate the magnitude, you always have to pick the smallest possible angle, right? It's true that the direction of the vector would flip if the angle is bigger than 180 degrees, but for calculation of the absolute value, it's not important. We need to make sure that sine theta here is non-negative. Yes, a question from Talia. So she's saying that the linear algebra was required. I don't believe so, right? So I don't. Yes. So the reason why I sort of invoke linear algebra is because when it's much easier to do it with that. So if you haven't taken it yet, I mean, it's not required, right? So I mean, it's true that it helps, but if you didn't take it, it's still okay, right? So let me try to explain the last proposition just by, but you can prove this by just only by looking at the definition here. So so Talia, look here. So the A cross B is this, and now so see every component, every term has a difference, right? That consists of say A2 B3 minus B3 A2, A3 B1 minus A1 B3. So now when you swap B and A, you swap the two vectors. Yeah, so let's write it down here. So B cross A. Then it will essentially change the sign to the -1, right? So now when you had A, you have B. So I'm just simply writing, if I had A2 B2, A2 B3, switch the color. Now it becomes B3 B2A3 and then minus A2B3 and so on, which is, and see the blue thing is -1 multiplied by the black thing. Yeah. But so I assume that at least you heard about the determinants, right? So Talia, is that the case? So do you know how to calculate the determinant of 3 by 3 matrix? Ah, good, good. Okay, yeah. So we are good. So we're not going to need any more linear algebra. I just, I think the cross product is all where it gets sort of used, but otherwise we're good. Okay, I think we're good. So let's prove this. Well, how we're going to prove it? Let's square left-hand side and right-hand side and show that they're the same. Right, so let's say have A cross B absolute value squared. How do you do that? Well, we just take the absolute value of those. We had the formula above, right? Let me just copy it here. So the first component was what? A2B3 minus A3B2 squared. Second component is A3B1 minus A1B3 squared. And the third component is A1B2 minus A2B1, everything squared. Now, well, you need to a little bit to do some calculations, but let's try to do them sort of in a smart way, right? So, what will we get from squares, right? So we'll have well, square of everything and cross terms, right? Now, how do you want to combine the cross terms? So the cross terms will appear with the factor of -2, right? So our idea is to rewrite this as the square of the right-hand side, right? So and the square of the right-hand side will be what? It's a absolute value a squared plus absolute value of b squared times sine squared theta. Right now, what is sine squared theta? Sine squared theta, we can rewrite it as 1 minus cosine squared theta. And cosine is, we can represent cosine using the dot product. So that will give us what? Absolute value of a squared times absolute value of b squared minus absolute value of a squared times absolute value of b squared. The cosine squared, and cosine squared is a dot b squared divided by the absolute values, right? So it's absolute value of a squared, absolute value of b squared. So we can cancel that. So this is the so this is cosine squared theta. So we can continue with the a squared b squared minus a dot b squared. And then, yeah, so we just need to show that, which is also, so a absolute value squared is a1 squared plus a2 squared plus a3 squared times b1 squared plus b2 squared plus b3 squared minus a dot b, everything squared, which is a1 b1 plus a2 b2 plus a3 b3 squared. And now we need to, well, open up parentheses here and on top and see that it's the same, that we get the same formula. Right. So let's maybe start with the bottom, since we're already doing this calculation. So see the terms coming from this first two parentheses will cancel some of the squares that come, it will cancel all the squares. Well, some of these terms will cancel all the squares that come from here, right? So here, second thing will give you 3 squares plus 3 cross terms. So all squares will cancel. And what will not cancel will look like this, right? So it will be, it's basically, it's a1 squared. So a1, b1 will cancel, and the rest will not, right? So it's a1 squared, b2 squared plus a1 squared, b3 squared. Write it like this. Plus a2 squared, b1 squared plus a2 squared, b3 squared, and plus a3 squared, a1 squared plus a3 squared, b1, sorry. Plus a3 squared, b2 squared, and minus, and here we only get the cross products, the mixed terms, minus twice a1, b1, a2, b2. So we can try to write them under each term, right? So it's here minus twice a1, b1, a2, b2, minus twice a2, b2, a3, b3, and the first row minus 2 a1, b1, a3, b3. And now you can see that every row here corresponds to the, let's get back to the top formula. You see that that this thing, the first term, corresponds to a2b3 plus a3b2 minus 2 they need to combine them differently, yeah. So it should be a3b2 a2 squared b3 squared, where is it? Purple, right? So this guy, that's 1 square, and a3b2, and this. So this, that, and that. Okay, so what I surrounded in purple matches, right? So 3 purple terms on the bottom match the purple term on top, and then that thing will give us what? a3b1, a1, b3, this guy, that guy, and that guy, right? And then finally, well, you don't think we have to surround it, but nevertheless, this will give you that. So yeah, so far so good. Everything matches and the statement is true. Questions? Now, the caveat about the sign was that, so we have proven that the squares, right? We have proven, so this proves that absolute value of a cross b squared is equal to this, right? So to the square times b squared times sine squared theta. Now, if you had to draw the conclusion about the values themselves, you need to take a square root, and then there are 2 branches, right? And because we select theta to be in this region, we have to pick the positive, the plus sign. Yeah. So all in all, we have proven this. That cross product of 2 vectors is equal to absolute value of this is equal to the length, the product of length is of two vectors times the sine of the angle between them. Okay, and similarly to the orthogonality condition for dot product, here we can draw the following proposition. Right, is that the two non-zero vectors are parallel if and only if their cross product is 0. Parallel to each other. If A cross B is equal to 0 as a 0 vector. So it has components 0, 0, 0. Right, so indeed, so if we have, if the vector is non-zero, then the angle between those, the sine of the angle between those vectors is defined by this cross product. And yeah, so therefore the sine is equal to 0. And that happens with only, so it's true because of proof, right? So the proposition implies that sine theta is equal to 0. So therefore it happens only when theta is equal to 0 or pi, which means that the vectors are parallel to each other. Questions? So yeah, let's do an example, and we'll show by example the following sort of. Let's illustrate this the proposition about the length geometrically. There's another proposition. Saying that this length of A cross B, right, is equal to the area of the parallelogram determined by a sort of built on A and B. To the area of the parallelogram built on, or based on rather, right? Proper word. Meaning the following, so if you put these vectors together, and then you draw, so this is A and B, you would complete a parallelogram, and the area of this parallelogram is A cross B, absolute value. Right? Well, the proof is pretty easy, right? So we take, let's make draw this altitude here, the height, right? And if the angle between two vectors is theta, then this thing is, the length of that is absolute value of B times sine theta. Right, and by construction, theta cannot be bigger than 180 degrees. Otherwise, you're not going to get a parallelogram. And then, of course, the area is equal to of this parallelogram, right? It's the it's just the product, right? So it's absolute value of A times absolute value of B times sine theta. Yeah. So yeah, that's it's the geometric meaning of the dot product. So of course we know that the vector A cross B itself will be perpendicular to this plane. It would be, you know, it would stick out. And yeah, so but its length measures the area of the parallelogram. Right, so this is something that is used in physics. You probably know that the laws of motion, the Kepler laws of motion of planets, or any bodies in gravitational field. It's sort of the fact that it moves on the ellipse. Sorry, the fact that these areas are conserved in physics is manifested in conservation of angular momentum. Because the force, which the gravitational force that acts on the object, is parallel to the radius vector. So therefore, the planet is not exhibiting any torque. And if there is no torque, then the angular momentum is conserved. And conservation of angular momentum translates into preserving areas that this radius vector smears as the planet travels around the sun. Yeah, sure, because, you know, this is the same, right? In previous proposition, we showed that absolute value of A cross B is equal to A dot B dot A, absolute value of A times absolute value of B times the sine of angle. Should solve for a given the vector and B. I mean, if you want to use this formula to find the angle, like we did with the cosine, yeah, you could do that. You could do that. Yes. Yeah. So what Cameron is alluding to. So, say you know the area, right, or whatever. So, and then you can find the sine of the angle by, well, inverting that, right? So sine of theta is A cross B divided by absolute value of A times absolute value of B. Yeah, that is true. Okay, let's maybe do one example to illustrate that. So let's find the area of the triangle with vertices well, I shall put the numbers, but okay, so let's even do, let's try to do kind of to do it for any numbers, right? So I'm gonna do it for any coordinates. So say you have 3 points in space, A, B, C, given by coordinates A1, A1, A2, A3, B1, B2, B3, C1, C2, C3. These are just the 3 points in space, right? And then of course you can draw a triangle by connecting all these vertices, right? So for example, let's do it here. Let's say this is A, this is B, this is C, right? And the triangle will be this, right? So it will have half of the area of the parallelogram, right? So, well, you just need to calculate the cross product. So the area of this triangle is half of AC cross AB absolute value, right? And then you just calculate the cross product, right? So it's IJK. See, I never memorized the formula because, you know, it's easier to make a sign mistake or something like that. And then here you would put what, so AC is what it's I think I need more space. So it's what, C1 minus A1, C2 minus A2, C3 minus A3, and AB is B1 minus A1, B2 minus A2, B3 minus A3, and this is I, J, K. So I just need to calculate the determinant of this matrix. Let me not write the full formula. Yeah, so like, but yeah, so like that's absolute value, and then you need to calculate absolute value of that, right? So, so that's and that's like it's like module of that thing. Absolute value of that vector, which will give us what is 1/2 square root. It will be a big square root with a well, basically, yeah, so do the calculation, right? Find the vector and calculate its square root. So let me not write the full formula. Instead, let's plug in some numbers, right? So let's maybe take the one that's from your book. So say point A is equal to say it's 1, 4, 6. This is -2, 5, -1, and this is 1, -1, 1. And then you can do it by yourself. If you do the calculation, you'll have a square 1/2 square root of -40 squared plus -15 squared plus 15 squared, and that gives you 5/2 square root of 82. Yeah, the calculation is straightforward. I think, and then before we close, let's talk about properties of scalar product, of cross product. So we started talking about the coordinate vectors I, J, K. Right, so we have found that I cross J is equal to K. And then you can also show that if you sort of do it in a circle, right, so J cross K is equal to I. And also K cross I will equal to J. You can prove it by applying the right-hand rule. Right, so remember, you start with a vector on the thumb, and then there's next is along the index finger, and then middle finger, which will show you the cross product. Right. So cross product is not non-commutative. So because, for example, if you do I cross J, right? So that will give you, so I cross J is equal to K. So it's I cross K. And that's equal to minus J, right? Because K cross I equals J. So therefore, we discussed it, right? If you flip the order of terms, I cross K will be minus J. So that's one calculation, but now let's try to do it yeah, so when it's non-commutative, we know this, and also non-associative, excuse me, yes, non-associative. Yes. Non-associative meaning that, so remember, associativity means that you have product of three things, you can put parentheses in two different ways. So if you do it like this, then you get minus J, but then if you do it I cross J, what is this equal to? What's I cross itself? 0, right? Because this is the sign of the angle is 0, right? So from the formula, so this is 0. And 0 is not equal to minus j. So associativity does not work. The other properties work. Okay, so we don't have, so we'll start the next lecture with summarizing the properties of course product. Any proofs or any last important things you would recommend to look over before quiz tomorrow? So no, we don't do any proofs. So quiz tomorrow will be just a sample of problems which are not as hard. I mean, they should be as easy as the homework, but not as computationally cumbersome. So you should not expect to have a long integral with many stages of calculation. So it should be something very transparent, just to test your knowledge of the first chapter. Yeah, so like right, so if you want extra review, like on top of the homework, you're welcome to look at the review exercises in section in chapter 10. Yes, so that's a good point. You can't find recorded lectures on B courses. So if you go to announcements, there are Zoom links. So they are not on B courses, the lectures are on Zoom, and you should have links to them. Should be linked, just put them in the. Yeah, I put the link in those announcements. Which lecture did we cover? Which lecture did we cover? 10.6 is what is the conical sections. So that was lecture 4. Is Wednesday recorded lecture up? I believe all lectures are. I believe all links are there. Like so, Christian. I mean, last Wednesday's lecture. Yeah, it's up. So check right away. So the. Just looking through the announcements. Yeah, I think they're all there. Right? So Wednesday, which day was that? Was 24th, right? Yeah. So there was an announcement. It's called Office Hours, Lectures, and Zoom link. It's there. Okay, good. So I'll see you tomorrow. So yeah. Thanks. Bye.